everyone. My name is Ralph Kaufman. I taught for many years at Fitchburg State University, and you wouldn't believe it, but I taught archaeology there, and today I'm going to be talking about geology. Now, what could an archaeologist say about geology? Well, I tell you, one of the interesting things about archaeology is that when we deal with long lost cultures that we are trying to resuscitate, probably the furthest back we can go, well, of course for Lucy, we're going about 3.4 million years. But today, I've been challenged by myself to do this for you, which is an incredible jump from 3.4 million years to 1.1 billion years. And the location of the site is in northwestern New Jersey. Now, one of the things I've been constantly involved with in archaeology is to preserve cultures. And we know that today many languages are being lost, but so too are many indigenous cultures being lost, not only for the information that they contain, but also for their artifacts. And so one of the things that we have been involved with in a project to recapture some of those lost artifacts is a study of what those cultures most in need of treatment are and how we can do that best. So today we're going to be talking about a long lost culture in northwestern New Jersey. And the interesting thing is, when you go to northwestern New Jersey, no one knows where this particular place is. As you can see, this is Franklin Furnace in Sterling Hill from about 1740, when the issues of mining in the area began, to about 1950, where most of the major mining ended. Was a tremendously interesting period in terms of the development not only of mining, but also of chemistry itself. In the northern part of New Jersey, there are several towns apart from Franklin Furnace, which is Franklin on the map here, and Ogdensburg, which is where Sterling Hill mines were located. All the other places on this map also have mines, that many of which were involved in producing iron for the American Revolution. Well, if they were beginning in 1740, by the Revolutionary period, they were really in full swing. But one of the things they began to find in this part of the world, although they had local resources. Now, if you're mining, ask yourself, what kind of local resources do you have to have? Well, one of the most important things is water, and the next thing is energy. They had plenty of forests where they could harvest wood and then produce charcoal from the wood, which gives you a higher heating temperature. Then you also need something with the actual ore itself. Actual ores require some way to take off all of the impurities. Well, one of the things you can use is limestone or marble. Limestone and marble will siphon off all of those impurities so that you're left with nothing but the pure metal that you want to extract. Iron ore, and then later on was zinc ore. Iron ore and zinc ore do not mix. These early miners found it out the hard way. When they began to smelt iron ore, if there was only iron minerals in the ore, they were fine. But once you begin to introduce zinc into that ore, you have a problem, because no longer does the marble or the limestone work as the adequate flux. So we have a problem, and the problem was begun to be solved. Here is Franklin Furnace iron ore smelting furnace, and notice that this is pretty primitive. It's made of fieldstone. I have a gentleman here who is standing beside it to give you some idea of how big it is. These are very interesting because the limestone is quarried in the area, so you have limestone or the marble. You also have the iron ore quarried in the area. It's crushed, washed, brought to your furnace, and then you put the two ingredients together, your ore plus your flux, and you have resultant pig iron. Well, that sounds fine, doesn't it? However, one of the things that happens, here I have the charcoal, I have the iron ore and I have the limestone. It works fine if I just have iron ore. But the fascinating thing, that zinc is found in many of these iron ores. Very unusual. What does that produce? Well, these old miners were pretty savvy about how you smelt iron, and they thought they had the idea. Well, we have zinc, we have the way in which zinc can work with our existing smelters, and we'll just put it in with the iron and there'll be no problem whatsoever. Wrong. One of the problems was that zinc, together with the iron, produces a very unusual product. These huge pink-colored, called salamanders, pink-colored chunks that are completely unusable. You can't put them into a mold, you can't use them as iron, and you can't use them as zinc. So they had a problem, and many of these old miners went bust because of this very reason. They thought they could figure out a way to do this. So we're talking about a period now in which the chemistry of mining, especially of mining and smelting zinc, was in its infancy. Even though many places had previously smelted zinc, they had not done so with the introduction of iron as a pollutant in its manufacturing process. So we have a problem. And what happened? Well, zinc mining became of age around 1854 when they discovered one process. You see, zinc has a low melting temperature, a low boiling temperature. And when it boils off into the atmosphere. Well, there goes all your ore and all of your metal. But you have a problem of trying to take that out of the atmosphere, so you have to have a closed container. Those closed containers were the answer to being able to smelt zinc. So there's a whole process of smelting zinc at high temperature, in which you have zinc or sodium chloride or zinc chloride in a sintering process, and the molten zinc comes out in beautiful iron pigs that you could use for your slabs. Now, the other invention of zinc smelting is an electrolytic process, but that wasn't developed until much later, and that's what this bottom part of the diagram indicates. So we had a beginning of metallurgy in northern New Jersey, where the zinc was being able to be used now in a variety of products. And it's very interesting because now the farmers in the local area, and I'm talking dairy farmers, needed, what did they need? Zinc plated pails, and they needed containers where they could send their zinc down the road to some big cooperative where the milk containers would be sent to their customers. So we have a new industry started that is in conjunction now with the dairy industry. Very interesting. However, nobody is really taking a look at all those things that have been siphoned off by the flux. What happens to those things? Well, it's an interesting thing. Here's a map of the two locations in northwestern New Jersey. You go to those towns, Ogdensburg and Franklin, and nobody knows. Where is Franklin Furnace? Nobody knows. Where is Sterling Hill in Ogdensburg? Nobody knows. But they should. And the reason is this. Stretching all the way from New Jersey, all the way through New York, up through Vermont, is an interesting orogeny. An orogeny happens to be the genesis of an ore body, and the ore body goes right straight through Dorset, Vermont. I know because I have a house there. Goes through Dorset, Vermont, all the way up into Ontario. How is this possible? There was a time when this part of the world was underwater environment 1.1 billion years ago. And what happened? An intrusion from the core of the earth of many complex molecules and atoms became in contact with marble that had been there for centuries, from old seashells that had been compressed, and also some limestone. And when the marble and these unusual molecules came in contact with each other, new minerals were born. In fact, more than 340 minerals are found in these two towns, as well as 80, probably above 80, unique minerals. Now, this is one layer area. This is Sterling Hill to the south, and notice it runs basically on a southwesterly to northeasterly direction, straight up through to Vermont and then to Ontario. And this is called the Grenville orogeny. It's an important orogeny because, although few people understand it and know about it, it has contained in it minerals that are exciting. Exciting because they get excited. And here's how they get excited. Number one, when you have a mineral that comes from this area that has a little zinc in it, you will find that if you subject that to short wave light, on the order a very short wave, we will find that the short wave coming in will excite the innermost electrons of these chemicals to an outer electron. And what happens? It goes to the outer electron over here, and we have a formula that allows us to be able to actually measure this. Energy, which is what's coming in, has a potential which is called Planck's constant. Well, you don't have to remember too much about Planck's constant, except that it is exciting because it's one photon of electromagnetic radiation. What's in the inner energy of one photon? Times its own frequency. If you know that, that's h nu. The little v there is a Greek letter, which means nu. H nu is the key to how much energy is needed to excite that electron to an outermost level. And it's out in the outermost level now. Another way of looking at it, maybe a complicated slide, but watch. It becomes so simple. Here comes our photon. Whoa, this is the light from our short wave. And the photon comes in, and notice what happens to our electron. One of them goes up high, another one goes up not so high, but they both come down to a resting level. In that resting level, as they come down, they emit some light. Whoa, that's kind of interesting. Can we see that light? Yes. And if you wait long enough, they come back down to their resting level. Ooh, can we see that light? Because you see, every time they give off light, they give off energy. Wow. And actually, I could measure that. So the little red arrow shows, wow, energy's being given off there too. So in both of these instances, we have these electrons being charged by the shortwave light that we are giving it. And then, as they get to their outermost level, they begin to drop, and we can see the light that they are emitting. Just think of it. Here we have a mineral. Doesn't look like anything. It looks like a rock you could pick up at the beach. Now, we subject that rock to shortwave radiation. I put the shortwave radiation over here, 254 nanometers. Those are very small amounts. And a nanometer is going to show you that the amount of light that we are shining on this particular specimen, well, look at the rock. It begins to glow. Why is it glowing? Because those electrons are going back to their original resting state, and you can watch them do that. However, this is the exciting thing. If you continue shining that short wave light on this rock, you will be able to see this totally glowing forever. It contains the energy from your short wave to keep those electrons constantly bouncing up to their next level and then descending. And as they descend, they let you know. Notice the color on this, by the way. This is yellow, and this one is called Wollastonite. It has a chemical composition that's calcium silicon trioxide. And calcium silicon trioxide is a pretty simple chemical, but except for the fact that it has these electrons able to be excited with shortwave radiation. We can take another one. This is paler yellow. In fact, it's so pale yellow, you would have to get up very close to see the pale yellow. However, notice this has a very complicated formula. It has magnesium, 4 oxygen molecules for the silicon molecule, and each one of those manganese molecules actually helps excite this to a pale yellow color. But it's not as bright as the previous one. So what does this show us? It shows us that we have 2 of the same color, but very different shades of that color. In other words, a very slight increase in the energy that these are picking up from that shortwave photon that we've directed at it. However, the third one is the brightest yellow you can imagine. In fact, this particular chemical called Sphalerite is so valued it's pretty expensive for people to sell today, but if you go down to Franklin Furnace, maybe you can find some in one of the slag heaps. In fact, they have a lot of slag heaps to go to, as well as Sterling Hill. Notice that if you looked at this regular rock on the beach, you would think, oh, maybe it's just quartz. No such luck. Look at how brilliant that yellow is, and next to the yellow is really a brilliant deep blue. The deep blue is calcite, a pretty common chemical, calcium carbonate, and it's a very beautiful color. So we have 3 different colors of yellow, all produced by the energizing of these electrons to their outermost state. We have another one. Now this happens to be, I think, one of the prettiest down at Franklin Furnace. It's one of the signature, and that goes a lot today to say signature what? Signature minerals for Franklin Furnace, because look at the colors. You have a brilliant orange-red color, which happens to be the calcium. We have the Willemite, which has green zinc in it. And we have black, which happens to be the zinc material that they couldn't get out of the old smelters. That's Franklinite, named for Franklin Furnace. Notice that there are 3 of them, and they're kind of very nicely interspersed with each other. So this happens to be one of the best of the Franklin Furnace examples, but here's another one. This is aragonite, which is pale blue. Now, this is really this brilliant blue. It's brilliant together with what you would be able to now recognize as the green Willemite and the orange-red calcite, and you would be able to see this is part of the Franklin Furnace combination, because you see the combination is the important thing. You have Willemite, you have the calcite, and you have an unusual material here, which is aragonite, calcium carbonate. Now, notice that calcium carbonate can occur as another mineral, but in this case, it's called aragonite because of its reflection of blue. Why is that possible? How is it possible? It's because what I'm not showing you here, there are some subsidiary ingredients in the calcium carbonate that is not indicated that allows this to be picking up a blue color when that electron comes down. So in many cases, when you take a look at a mineral, it's not purely calcium carbonate, but it is calcium and carbon and oxygen plus some impurities. And then we have a very pretty one, and this is one in which we have Willemite together with the red that we saw before, the calcite, and the black Franklinite. But notice that in this specimen, minerals are splotchy. They're not evenly spaced, which is to say that in the original formation of this orogeny, as it came from the core of the Earth through the crust, what we have now is a different combination. It produced a different way in which the minerals aligned themselves with each other. So in this examination of these minerals from Franklin Furnace and Sterling Hill, I hope you have gained an appreciation of just how important shortwave light is for showing how some of our minerals that we find on the beach or in places that we go for vacations could be possibly enhanced if you took a light with you in the middle of the night, going out and seeing what they are in nature. Thank you very much, and I'd appreciate any questions. I've gone around the world in examining rare minerals from Namibia to Western Europe to China. I've found that these minerals in Sterling Hill are among the most fascinating that I've come across. The way in which we have been able to provide them here is through the generosity of the people down at Sterling Hill and Franklin Furnace, who have allowed us to have a small collection of their magnificent collections that they have on display at the two museums in both Sterling Hill and Franklin Furnace towns. So I heartily invite everyone to take a look at those museums because they have staff on board, and you can also request to have some of the rocks that they have in their old slag pits donated to you for a modest fee of $1.50 a pound. So I strongly urge you to go down there and take a look. They're excellent for children and adults of all ages. When these minerals were first investigated, they were produced in 2 volumes, very intricate geochemistry. And the geochemistry did 2 things. It actually identified the crystalline structure, and not only the crystalline structure, but also the reflected light. So these volumes, Franklin and Sterling Hill, New Jersey, the Bibles for understanding the most recent, current, up-to-date information on these minerals. 1950 is an interesting date because it was at that time that Lilly discovered the radiocarbon decay of carbon-14. And a lot of excitement was in the wind among chemists and physicists and geologists about what other kinds of minerals would there be that we could investigate in new and different ways. So around 1950, a group from Harvard University geology department went down and collected some samples, brought them back to the lab, and began experimenting. At first, the results were mediocre. Yes, some things were unusual, but they didn't really produce any spectacular results until they began to experiment with applying different kinds of energy to the molecules that were these unique minerals. When they did that, unique occurrences occurred. We're going to go into the laboratory where I have arranged these minerals according to various types of occurrences that produce different kinds of wavelengths that reflect off these minerals. Take a look at them in natural light. We don't really see too much. We see a lot of minerals, but we don't really see anything spectacular. So we have to inject a little energy into these fellows so that we'll be able to have a type of energy increase so that the energy actually is taken into that outermost electron. And as it is taken in, some of these electrons actually continue to spin in that excited state after I turn off this light. And we can see there is light still being emitted. Now, the first evidence of this is due to fluorescence. But when I turn off the light and there's continued excitation of that outermost electron, that is phosphorescence. That means that outermost electron cloud is able to store the energy from this special shortwave light at around 2500 angstroms. So here are a couple of the technical names that we call these things. The purple is Wollastonite, the yellow is Diopside, and this is a typically rare mineral not found outside Franklin Furnace, Sterling Hill. This one is called Flouro Ignite. Flouro Ignite suggests it comes from fluoride, and as fluoride, it is phosphorescent. But Ignite is a special version of fluorite. We have this one, which is Sphalerite, Calcite, and Willemite, which is green. Calcite's red, Willemite's green, and those are unusual in that combination. And then this one is diopside and calcite, which is blue. If you take a look at these minerals, Wollastonite in this particular mineral have different intensities. One has certainly a lot more Wollastonite in it, which is yellow, and this one has crystals of Wollastonite that are embedded in a matrix. In another example over here, which is also yellow, this is from the area of Sterling Hill, and you can see the yellow Wollastonite also embedded as crystals. Over here we have green and Willemite, and orange, which happens to be calcite. These right here are mainly calcite with some Willemite, which is green, but they are all from Franklin Furnace. So you can see the intensity of the reflected light varies with the individual specimen. Then, when you have a much more rose-colored hue, those are entirely different minerals having nothing to do with calcite. They are called margarite. Those minerals are extremely complex. So in your following of these various minerals, you will be able to find various minerals that have different intensities of reflected light. Reflected light tells us that the electron cloud in the outermost ring does able to store energy and reflect it back to us. But some of that reflected light can actually be stored in the mineral crystals itself, and therefore you have phosphorescence. I just returned from North Carolina, where we did voter registration for many communities. The communities range from Raleigh, which is in the Research Triangle, to the research towns with universities like Durham and other University of North Carolina at Chapel Hill. Students were very much in favor of going out and helping us do registration of voting. And then we went to other locations which happen to be outside of the Research Triangle, and these are communities that have been left behind. Now, the critical thing about these communities that have been left behind is we can't ignore them. They have people who have real problems economically and geographically because they no longer have access to factories and other places of employment that were there 10, 15 years ago. So in interviewing those people, they had entirely different ideas about what their political agenda would be for the United States, and they were all for keeping the production of manufacturing within the 48-state border and within the confines of a way in which jobs wouldn't be trickled out to China and India. Many of these people had worked in factories all their lives, and it was devastating to see how their lives had been ruined just by factors that they have no control over. And in fact, I think that was the most egregious point of their messages. They feel that they are helpless with regard to globalization. So I only recommend to all of my fellow Americans that we please give these people their due accord and recognize that they have genuine concerns that must be addressed, whoever is elected president. So we got in touch with the Hillary Clinton office in downtown Fayetteville. We had them set us up with the various communities that they had identified as being critical for their success. We took those into due account, but as I indicated, we also took into account those communities that were not listed on their list of critical communities. So by putting the two together, we got a picture of what things are like in North Carolina and why it is so fractionated. We wanted to get people to get out and vote. Today we're going to be taking a look at two mines, one Sterling Hill and one Franklin Furnace in northwestern New Jersey, both of which were discovered in the 1700s and during the War of Independence were used for the extraction of iron ore. During the period of that war, the iron ore was used for various types of cannon, and muskets. But the real issue of the mine was not to surface until much later, about 100 years later. In about 1780, the mine fell into disrepair because it became too expensive economically to extract the iron ore from the various types of ores that were found in this particular series of veins. The veins are orogenic, that is to say, they're genesis of ores that occur in response to the way in which core elements within the Earth's central molten mass, from time to time, have their exposition in various types of dikes that come up through the existing crust of the Earth. Now, it was just so happened that this particular ore body was 7 miles long and about 2 miles wide. And as you saw in the map, the two ore bodies, one located in the southwest, Sterling Hill, and in the northeast, Franklin Furnace, were associated with an occurrence of rare minerals that had come in contact with various calcium carbonates, old seashells that had been under metamorphosis, producing various types of marble and calcium carbonates such as various types of limestone. Now, the interesting thing is that nowhere else on planet Earth that we know of today had this occurrence. Why? Well, because it was an early occurrence 1.1 billion years ago in which this genesis of ore bodies actually came in contact with the calcium carbonates, and they produced unusual minerals. In fact, of the 3,500 minerals on planet Earth, 80 are found in Franklin Furnace and Sterling Hill, and 30 are located in Franklin Furnace alone. After the War of Independence, the mines went into disuse, and about 100 years later, as the inventive New England farmers began to peddle their milk from the various herd animals that they had, they realized that they needed something to transport the milk in. And what would be better than to transport it in something that wouldn't rust? Well, one of the minerals that was contained in this ore body was zinc. So around 1880, the idea of hydroplating zinc onto iron became a source of income for these two communities, and they continued on in this capacity until about 1950. Around 1950, a group from Harvard University geology department went down and collected some samples, brought them back to the lab, and began experimenting. At first, the results were mediocre. Yes, some things were unusual, but they didn't really produce any spectacular results until they began to experiment with applying different kinds of energy to the molecules that were these unique minerals. When they did that, unique occurrences occurred. So we're going to go into the laboratory where I have arranged these minerals according to various types of occurrences that produce different kinds of wavelengths. Now we're going to go over here behind you.
Okay.
Just to make it a little more difficult.
Right.
And
Oh, you're going over here. Okay.
right. I'm going to show you some minerals that you should look up in the book. And the first one I want to focus on is Wollastonite.